Hello, my name is Alexey Veselov, and I want to tell you about my scientific research. I work in the Institute of Applied Physics, Russian Academy of Science, in the laboratory of applied plasma physics, so we have a lot of experience with it. Our experiments concerned only discharge-produced plasma and its application. The term gas discharge originates with the process of discharge of a capacitor into a circuit incorporating gap between electrodes. If the voltage is sufficiently high, the electric breakdown occurs in the gas and ionized state is formed. Later, the term discharge was applied to any flow of electric current through ionized gas by the applied electric field. As gases ionize to a sufficient degree, emit light, it has become customary to say that the discharge lights up or is burning. How does the discharge happen? A relatively simple experiment introduces us to several fundamental types of discharge. Two metal electrodes connected to a DC power supply are inserted into a glass tube. The tube can be evacuated and filled with various gases at different pressures. The quantities measured in the experiments are the voltage between the electrodes and the current in the circuit. If a low voltage is applied to the electrodes, no visible effects are produced. Only a super-sensitive instruments would record any extremely low current. Charges are generated in the gas by cosmic rays and natural radioactivity. As the voltage is raised further, the current sharply increased at a certain value of voltage and light emission is observed. These are the manifestation of breakdown. Breakdown starts with a small number of spurious electrons or electrons injected intentionally to stimulate the process. Their discharge becomes self-sustaining. The energy of electrons increases while they move in the field. Having reached the atomic ionization potential, the electron spends this energy of knocking out another electrons. Two slow electrons are thus produced, which go on to repeat the cycle described above. The result is an electron avalanche. The gas is appreciably ionized in time less than a microsecond, which is sufficient for the current to grow by several orders of magnitude. The electric breakdown threshold is determined by the relation between creation and removal of electron. Discharges in a DC electric field can be classified into self-sustaining glow and arc discharges. Townsend's dark discharge, it proceeds with a cold cathode and at very weak current. The corona discharge, corona has common features with glow and dark discharges, and the last one is the spark discharge. In our laboratory, we focused on a study of gigahertz radiation-produced plasma. The frequency range is characterized by a small amplitude of electron vibration, which is much more smaller than the discharge volume. As a result, the evolution of an electron avalanche is localized and almost independent. In that case, the threshold field as a function of pressure always has a minimum. On the left-hand branch, the threshold decreases with increasing pressure. This threshold is lower the greater the discharge volume and the lower field frequency. On the right-hand branch, the dependence of electric field density on size and frequency becomes less and less, and almost vanishes at the limit of high pressures. At present, the terahertz frequency range is still the least studied from the point of view of gas discharge physics. The study of the discharge sustained by the powerful focused beam of terahertz radiation has become possible recently due to the development of powerful sources in this range, FELS and gyrotrons, and is of interest both from a fundamental research and from possible application. Now I want to demonstrate our experimental setup. Experiments were carried out on a setup with pulse gyrotron with a frequency of 0.67 THz and pulse duration 40 microseconds. The terahertz radiation from the exit window of the gyrotron is converted into a Gaussian beam by a quasi-optical converter and is focused into the center of the chamber, which is filled with a working gas. The radiation power in the beam in the center of the discharge chamber was 40 kilowatts. It was measured using a calorimeter. In order to eliminate the influence of external impurities, first of all, its oxygen from the atmosphere, the chamber was preliminarily pumped out to a pressure of 10 in power minus 6 torr using a turbomolecular pump. In the center of the chamber, in the beam waist, there was an additional focusing mirror, which allowed increasing the local electric field density. On the slide, you can see a characteristic integral photo of the discharge in the chamber. It has a fishbone-like structure which follows the electric field distribution of the Gaussian beam. The color of the discharge depends on the background gas. Each gas, depending on its atomic structure, emits certain wavelengths, its emission spectrum, which determines the color of the light from the discharge. Emission spectrum also depends from the gas pressure. The lower the pressure, the shorter wavelength radiation is emitted from the discharge. It's concerned with the formation of multi-charged ions. And now I want to show you several examples of the discharges. Helium discharge has a white to orange color. Under some condition may be gray, blue or greenish blue. Neon discharge has a white to orange color. Argon discharge has a violet to pale lavender blue color. Krypton is gray, of white to green, and at high peak currents is bright bluish white. Xenon gray or bluish gray, dim white. At high peak current, very bright greenish blue. Nitrogen is similar to argon, but duller, more pink. At high peak currents, bright bluish white. Mercury vapor is light blue, and the discharge emits intense ultraviolet radiation. But how we could use discharge in everyday life? We propose to use discharge plasma supported by terahertz radiation as a source of extreme ultraviolet light for high-resolution lithography. An increase in plasma density to a value 10 in power 15 per cubic centimeter and above, with increasing frequency of the heating wave, makes a plasma resonance heating mechanism effective with small plasma size. The main idea of creating of a point discharge with high emissivity in the required wavelength band is the realization of a breakdown in a non-uniform gas jet with a scale of inhomogeneity of order of 1 mm. In this case, breakdown condition fulfilled only in a small region of space and discharge cannot go beyond it. The scheme of the experiment is present on the slide. Typical photo of the discharge is present on the second figure. In the optimal condition for extreme ultraviolet light generation, the point-like discharge emits about 100 Watt per cubic centimeter in the range from 12 to 17 nanometer. That can be caused of the fact that temperature in the center of the discharge is high enough to generate ultraviolet photons. So, with running to the short wavelength area, plasma starts to be invisible for the camera. Unfortunately, the efficiency of that process was about 1/100th of a percent, but further experiment on Novosibirsk fell can demonstrate better result. And is this the only gas discharge plasma application? Of course no. One more application of it is a disintegration of a carbon dioxide. Over the past few years, the concentration of carbon dioxide, which is one of the main greenhouse gases in the Earth's atmosphere, continues to grow at an increasing rate. Such a dynamic increase of carbon dioxide in the atmosphere over the coming decades will lead to global climate change with an increase in global temperature by 2 degrees Celsius. The enormous efforts of all countries are currently aimed at reducing carbon dioxide emission by eliminating the burning of fossil hydrocarbons and the transition to renewable energy sources. That is why there is currently a huge demand in the world for the search for carbon dioxide utilization technologies. To date, traditional methods of electrochemical conversion, photochemical conversion, biochemical conversion, catalytic chemistry, each of which has its advantages and disadvantages, are actively developing. The disadvantages are mainly related to the low energy efficiency of the methods and the need to use expensive catalysts that have a limited lifetime due to the surface poisoning. Thermal equilibrium plasma, in which all of its components are characterized by the same temperature, has low energy efficiency in gas conversion application, since it's necessary to maintain a high temperature of the entire gas volume. At high gas temperatures, the role of reverse reaction also increases in the case of carbon dioxide. The limiting degree of conversion and maximum energy efficiency reach a limit of 80% at a gas temperature of 3500 degrees Kelvin. That is why the most promising of plasma methods is the use of non-equilibrium plasma, characterized primarily by significantly higher electron temperature. The most developed in application to the task of gas conversion today are non-equilibrium plasma of a gliding arc discharge, of a dielectric barrier discharge, and a microwave discharge. Studies on the decomposition of carbon dioxide molecules into carbon dioxide and oxygen began in the 1980s with the pioneering work of Friedman, in which record values of carbon dioxide conversion and energy efficiency were obtained in a microwave discharge in a subsonic gas flow at pressures 100 torr. In our experiments on the decomposition of carbon dioxide, the technological gyratron with a radiation frequency of 24 GHz and output power of up to 5 kW in the continuous mode was used as a source of microwave radiation. The experimental setup is shown on the slide. The generated radiation along a circular waveguide was converted to a Gaussian beam with linear polarization. The radiation is introduced into the gas chamber through a cooled window. The parabolic mirror was used to increase the energy flux density. The radiation intensity in this area reached 5 kW through square centimeter at a maximum output power of gyratron. The end of the metal tube was led to the beam waste region. This tube was used to supply the plasma forming gas. The best result on the composition of carbon dioxide were achieved in flow of gas mixture of argon and carbon dioxide. The chemical composition of the gases was measured using a quadrupole mass spectrometer. When the plasma is ignited, the peak with mass 44, which corresponds to carbon dioxide, is decreasing, while the peak with masses 28, carbon monoxide, and 32, oxygen, are increasing. The conversion efficiency was estimated by the ratio of carbon dioxide signal with and without plasma. It is seen from the small figure that carbon dioxide conversion is in the range from 25 to 40%, while the efficiency reaches maximum of 70% at 900 watts. Well, on this application I decided to end my speech. I hope that I was able to convince you that gas discharge physics covers a great variety of complex and multi-phased phenomena. It's full of enormous amount of experimental facts and theoretical models.